different phases of matter, and matter can be defined simply. It's really anything that takes up space and has mass to it. So now, let's think about this for a second. My table. Do you guys think my table is an example of matter? Yeah, it is, because it takes up space and it has some mass to it. So now, matter is made up of these little tiny particles called atoms and molecules. My atoms, they come together and they form the molecule. And depending on how heat is added or how heat is taken away, my atoms and molecules go into different phases. Now, who wants to tell me 3 common phases in matter? Solid, liquid, and gas. Exactly. So, now, do you guys think that these
Solid,
are all
liquid, gas.
the same? Are all the blue dots equally spread apart? You can shout it out. No, right? So, if we take a look at the solid, all the little blue particles representing our atoms and molecules, they're really, really close together. But if we go into our liquid, these atoms and molecules get a little bit farther apart. But what's so different about our gas?
The gases, molecules, and kinetic energy are really far apart.
Yeah, that's really good. So our gas molecules are really, really far apart. So now, I want you guys to think about penguins for a second. Penguins, when they're in the cold, do they come to huddle together, or do they go far apart from each other?
Far apart.
Far apart? If it's really, really cold, do they come to huddle, or not really? They come to huddle, right? Because they want to keep warm. That's how my atoms and molecules are going to act too. When we take away heat from them, they're going to come closer and closer together. And if we add heat to them, they're going to come far and far apart. So now let's think about it. Say you're in a really, really hot school bus. Who here has gone in a school bus before? Or a regular bus? Yeah, I'd say a good amount of you guys have all gone into a bus. So if it's really, really hot in that bus, do you want to be really super close next to the other person? Or no, right? It's very uncomfortable. My atoms and molecules are like that too. Okay, yeah. Yeah, okay. So my atoms and molecules act like that too. They're going to come farther and farther apart if there's too much heat around. So now, do you guys want to test out these theories?
Yeah.
Yeah. Alright, so I have this pot here, but I also have 3 balloons. Do you guys think that I can fit all of these balloons into this one pot? No? Well, let's try it out, anyways. Let's see. 1 balloon can fit. Can I fit another balloon, you think? Maybe? Let's test that out. Oh, I don't think it's working. But that's okay, because today we're going to be working with this really cold, special substance that I'm going to take out, and we're going to see what happens when I put it inside. I want you guys to take a really, really close look at what happens to my pot. And what do you guys see coming out?
Oh my God.
Water?
Oh, is it nitrogen?
Those are all really great guesses, but I want you guys to remember, my substance is really, really cold.
Solid ice?
Now we're going to try and put in our balloon. Let's see.
Yes.
What do you guys notice happened to my balloon?
It's shrinking.
It's shrinking. Yeah. So our atoms and molecules, because we're putting it in this really, really cold area, are we adding heat or are we taking away
We're
heat?
taking it away.
We're taking away heat. So now, do you guys think we can fit these other 2 balloons in there?
Yeah.
Yeah? Let's test that out. Let's see.
I can hear it crumbling.
Okay. We've got our second balloon in. And now, do you guys think we can fit in our last balloon?
Yes.
Maybe? Okay, let's take a look. And we can fit it.
Oh, yeah.
So, because we put our balloons into this really, really cold temperature, all of its atoms and molecules, do they come closer together or do they go far apart? Closer, exactly. So, now, before I put Now, I'm going to show you guys what happens when I take out my balloons from this really cool substance. Take close attention.
Oh my god!
What's happening? చూడు మళ్ళీ బ్లూ
Right? Well, they were always balloons, but we had gas before, but then they became really, really small, which is what I'm going to show you guys happened last week. All right, I'm going to come around, and I need you guys to take good close attention to what's at the bottom.
చూడు
Do you guys see anything at the bottom of there? Okay, that's a good guess. There's some liquid down there, yeah.
H2O!
Great guesses, guys. So, yes, inside of this clear balloon, we had all of our gases. And I'm not sure if you guys could have seen it, but there were also some shards of carbon dioxide. Now, the liquid that you guys saw in there was the nitrogen and the oxygen that we were talking about. So that's really cool. When we took it away from that really cold substance that I had here, did we add heat or did we take away heat? When I took it out, we added heat because the air around us is a lot warmer compared to this really, really cold special substance. Now that we have tested stuff using our inflated balloons, do you guys want to test something out with a deflated balloon? Yeah. I think I want to too. So now I have this balloon. And I want you guys to notice what I'm going to do with it right now. What am I doing?
You're stretching!
I'm stretching it. But why am I even stretching? Well, that's really because my balloon has this property called elasticity. Now, elasticity is basically an object's ability to change shape and then return back to its original form. So, if I was to pull it like this, would it stay like this or would it snap back? It would snap back. Exactly. Now, do you guys think that my rubber mallet here has elasticity?
No!
Well, that's a really tough question, but believe it or not, my rubber mallet actually does have elasticity, just not as much as my rubber balloon. Now, do you guys think that I'll be able to smash this balloon and break it?
No!
No? Well, let's have some faith. Ready? Let's give it a countdown. 5, 4, 3, 2, 1. I'm sorry, guys. I'm not strong enough just with this. But wait, we have that really special substance with us. What would happen if I put it inside?
It will freeze! It will crumble!
Let's take a look. So, when I'm putting this undeflated balloon, I'm putting it into this really cold substance. So am I adding heat or am I taking away heat? Taking it away. So now all of these atoms and molecules, are they going to come closer together or farther apart? Closer together, exactly. So now on the count of 3, I want you guys to give me a countdown really loud and I'm going to try to break it again. All right? So 3, 2, 1. Wait, well I wasn't able to break it before. Well, let's talk about that for a second. Because I put it in this really cold substance, I took away my balloon's property of elasticity, calling it something as we know, brittle. Brittle is basically an object when it defines something that is really easy to break. elasticity back. So now, I want you guys, now we've been talking a lot about this really special substance, but I haven't told you what it is yet.
Nitrogen.
I heard some really good guesses.
Liquid.
So, I'm going to pour it in here, and I want you guys to tell me what you notice happened.
Wait, I can't
Okay. All right, we're going to let
It's boiling.
It's boiling, exactly. So that's something that we're going to be talking about today. So how is it boiling though? I'm not putting any other heat. So where's it getting the heat from? Is it getting it from the table? No. Is it getting it from the air around us? Yes, because the air around us is really, really hot compared to this really cold substance. Now, my substance here boils at negative 320 degrees Fahrenheit, which means our air around us is a lot warmer. And now, tell me, do you guys see any bubbles in here? Yeah. What else do we see coming off of it?
Water vapor.
Okay, yeah, we see some vapor coming off of it. Now, this is called what we call boiling cold. Now, I have something else that's boiling on my team. Does anyone want to tell me what they think it is? You can shout it out. Water! Exactly. Well, how'd you know it was boiling?
The bubbles.
Yes, the bubbles and the steam. So, the bubbles and the vapor that we see coming off of it are our two indicators that something is boiling. So now, we're going to talk a little bit about this boiling water first. So, does anyone know what the boiling point of water is? In Fahrenheit or in Celsius? I'll give you guys a hint. It's over 100 degrees Fahrenheit. Take any guesses.
110.
Okay, I'll give you guys a little bit more. It's over 200 degrees Fahrenheit. 212 degrees Fahrenheit. Exactly. Alright, thanks guys. So, I heard the right answer. And even though all of your guesses were really close, this water boils at 212 degrees Fahrenheit. But for us to get it to seem like it's boiling and for you to see those bubbles, it was boiling at a lot hotter temperature. But that is our boiling point. Now, this is what we call boiling hot. Now, these two substances are really, really different. One is super, super hot, and one is super, super cold. Do you guys think it would be a good idea if we mixed them? Okay. So I heard some yeses and I heard some no's, but I think I want to mix them together so that we can see what happens. So now we're gonna see what happens. Okay. I'm gonna add some more of our currently liquid nitrogen into our pot so that we can get a good reaction. Whoa, we see a lot of that vapor coming off. Okay. Now, from the count of 10, I'm going to pour in this really hot water into a really cold liquid nitrogen. Okay? So I want you guys to start giving me that countdown.
10, 9, 8, 7, 6, 5, 4, 3, 2,
have it here, and I'm going to come around and show you guys what was left. I want you guys to take really close attention.
Solid ice.
Ice.
So we did have a lot of ice in here now. But where did the ice come from?
From the heat and from the heat and nitrogen.
Yes, the water did become ice. Because our liquid nitrogen is super cold, it froze our ice almost instantly. Now, let's think about this. Does anyone know the freezing point of water? 0 Celsius and
110 degrees Fahrenheit.
exactly 32 degrees Fahrenheit. So that's a really, really different temperature compared to our negative 320 degrees Fahrenheit liquid nitrogen and our 212 degrees Fahrenheit boiling water. So who here has ever put ice in, has ever put water inside of their freezer to make ice? Yeah? Does it take a long time or does it take a short time? It takes a long time. Yeah, sometimes when I have a soccer game, I have to put in some really cool plastic water bottle that I have. I throw it in, I leave it overnight, and then I come back and I take it out, but it's a bit puffy around. But I thought that when we took away heat, all of its atoms and molecules were supposed to come closer and closer together. So shouldn't it come and kind of crush the water bottle? Well, that's something that's really special about our water. Now, our water has this cool property of hydrogen bonding. Now, hydrogen bonding, you would think that that means that all of our water molecules are going to come close and close together, but really they're going to expand into what we know as ice and form that ice structure. So now that we've seen all of these really cool experiments and seen how matter changes from phase to phase, I'm going to give you guys a quick little recap of everything that we've talked about. So when I take away heat, are my atoms and molecules going farther apart or are they coming closer together?
Close.
Closer together. They're coming closer together because we're taking away that heat. Think about our penguins. Are they going to come close together or far apart if they're cold? They're going to come close together. And now, if I add a lot of heat, are my atoms and molecules going to come far apart or close together?
Far apart.
Far apart. Exactly. So, thank you guys for being such a great audience, and I hope you guys enjoyed the rest of the day at the museum. And if you have any questions, you guys can come up and ask them.
Thank you so much.